Hello, welcome to the last lecture on the topic of state space analysis. So today we will be working with multi-degree of freedom system, and we want to do vibration aka frequency analysis for these systems. So the overall goal is to characterize the vibration or frequency behavior of a multi-degree of freedom system. Specifically, we want to know how the behavior of these systems in vibration, how the system essentially vibrates using a state space modeling. So to begin, let's look at, again, as always, a very simple case, and this is our companion in all these examples, the mass spring system. Here we are leaving the damper behind just to have a system that oscillates forever. So the equations of motion for this system, we have seen it many times. My double dot equals minus ky. So if you pull it y in positive direction, the force of the spring wants to pull you back. Or I can write it as y double dot is a constant times y. So what we are dealing with here is something called an eigen problem. We discussed it before, that for any operator, in this case our operator is second derivative, that takes one function. The operator takes second derivative of it and outputs something. You can, for any of these operators, you can try to find a function, or whatever the operator takes. In this case, the operator takes a function, outputs another function. You want to know what function you can feed it to the operator, to the second derivative, and the output that comes out is a similar shape of the original input function. So this is an eigen problem. And the eigenvector problem was working with the operator of matrix or linear transformations. And it was working on a vector space. And the eigen problem in that case was what vector, when you multiply it or transform it through the matrix A, remains similar version of itself. So only a scaled version of itself along the same direction. So that was another eigen problem. Here we are dealing with a problem working in a function domain. The input is function. And for the second derivative, one of the solutions for this eigen problem is y equal sine of omega t. So if you take the second derivative of this, so y dot, first derivative will be cosine of omega t, and second derivative will be minus, I'm missing omega. It's going to be omega sine of omega t, and omega cosine of omega t, and then derivative of this will be minus omega squared sine of omega t. So you see, if I give in, the input is in the shape of sine, the output will also be in the shape of sine, but only a scaled version of it. So that's a solution to this eigen problem for the operator of second derivative. And quote unquote the eigenvalue of this, we can calculate it. So I can plug it here. So y double dot minus omega squared sine of omega t is going to be equal to minus k over m times y, which is again sine of omega t. And from here, you can calculate the eigenvalue of this eigen problem. Omega squared equals k over m, or something we had seen before, we called it natural frequency, omega is square root of k over m. So we solved this eigenproblem. We calculated the eigenvalue of it to be the natural frequency of the system. But that is kind of just opening. I wanted to show you how you can relate the ideas of eigenproblem to find the natural frequencies of the system. We also did the same thing with a different eigenproblem. So if I write this system in a state space form, I can write my x1, my first state, to be position, my second state to be y dot. And if I do that, my state space equation, x dot 1, x dot 2 will be 0, 1, what do I have, minus k over m, 0 times x1 and x2. And we kind of know that whenever we have this, a lot of information comes out of this eigenvalues and eigenvectors of this matrix A. So let me calculate that. What I need to do is to get the determinant of A minus lambda I to be 0, my characteristic equation for that. So this one is going to be determinant of, what do I have? So A is 0, 1 minus lambda minus k over m. No, why am I doing this? A minus, oh, I have minus lambda, 1 minus k over m minus lambda. This is 0, determinant of that. So what I have is lambda squared plus k over m equals 0. And from here, I calculate lambda. So if I take the k over m to the other side, it's going to be negative at taking a square root of a negative number. I have plus minus j square root of k over m. Again, a lot of information we could obtain out of the eigenvalue. It's the same, I get the same natural frequency, but it has more information in it, that it is now a complex number, meaning that there are rotations, aka there is this oscillation at that specific frequency. And we shouldn't be really surprised to see this, because we knew the eigenvalues of matrix A. This define the modes of behavior of the system. We know that this system oscillates forever, and the mode that is associated with non-ending oscillation is just a rotation about just a rotation without any dying down, without any real part. So this lambda shouldn't have any real component, and it should have some imaginary component, and the speed of rotation is the natural frequency of the system. So this is by no means probably a surprising result for you. But we can go further. Maybe the rest is a little new. Now let's calculate the eigenvectors of this matrix. So to do that, I can write A times V equals lambda V. yeah, let's write it down. So for my lambda 1 to be j omega n, so I'm just going to write it as plus minus j omega n, same definition as down here. So for this, I can write 0, 1 minus k over m, or I can write it as minus omega n squared. And 0 times my vector, I'm going to write it as a and b, which I want to find, equals lambda j omega times a and b. So I have this set of set of equations. So I have 0a plus b equals j omega b, the first line. So b equals j omega a, and the second one minus omega n squared a equals j omega b. These are the two equations. And one thing to notice here, if I multiplied the first one by a j omega, let me do that. Multiply this by j omega, so I'll have j omega b equals this j omega multiplied by another j omega will be omega squared times j squared, but j squared is minus 1 equals a, and it's the same equation I had before. So it is expected, because the term, specifically because we are looking at an eigenvalue. Eigenvalue makes determinant of this a minus lambda I 0. So this equation is fundamentally ill-posed. You cannot solve it. It has infinite solutions. So to do that, you can simply, so it has infinite solution. You can take any value for a, and b, you can find a corresponding b value. So I'm going to take a equal 1. And from here, my b is going to be j omega. So the first eigenvector is 1 and j omega. And the second one, so this one is accompanied by lambda 1 equals j omega. The second one, b2, is, what is it going? It's going to be complex conjugate of that. So 1 and minus j omega here. For the complex conjugate, lambda 2 equals minus j omega. And you can easily check this. So if this is minus, that becomes minus. Well, this one also becomes minus. That one becomes minus. So if I take a, b becomes minus j omega. And these are kind of interesting, at least to me, to look at them. So for j omega, rotation in a positive direction, I came up with this eigenvector. Let me try to visualize that. So let's look at the complex plane. And what I have here is I have a vector. Let me write it down again here. V1 equals 1 and j omega. So it was a vector in this domain, right? It is the vector that is acting in the x1 and x2 domain, or in the position and velocity domain. So the first element is related to position, and the second one is related to velocity. Because the first dimension is related to position, the second dimension is related to velocity. So here, if I want to visualize this, I can use something called phasor plot that some of you may remember from the electrical engineering courses. So what I can do is draw my position vector. Position vector is just 1, so it's a real number. Let me draw it with a different color. So this is my position vector. Make that red also. And my velocity vector, the component, the complex number that is in the velocity position, in the velocity kind of element, I have too many positions, is, let me make that j omega, and this is the velocity phasor. So this is velocity phasor, or V, and this one is position phasor. And what happens is as time goes on, I have too many markers. So the response is going to be V1 times e to lambda 1 j omega t. So remember, this is a rotation that essentially is rotating this vector v, which means my phasors will rotate with the rate omega. Omega n. Why am I dropping all the omega n? Am I missing any n? And this is omega n. So my system, my phasor plots are rotating because they are being multiplied by this e to the j omega n, and it means that my position goes back and forth. So as I rotate this, my position goes back and forth, and my velocity also goes back and forth, but my velocity will always remain 90 degrees ahead of my position, which makes sense if you write your system, your y, which is sine of omega n t, your velocity y dot will be omega n cosine of omega n t, or sine of omega n t plus 90 degrees. So my velocity, same thing as happening here, is always 90 degrees ahead of my position. So this is a way you can try to figure out what is the relative kind of phase of the position and velocity when you have these oscillation. In a 1 degree of freedom system, this is more or less trivial, that you would expect this. But I hope this concept of kind of visualizing with phasor makes sense. it will be more interesting when we add more degrees of freedom to the system, and we can get a lot more information by looking at these phasors. So let me clean up the board, and I can come back with a 2 degrees of freedom system and start to analyze that. So let me do that, and I'll be back. Now let's take a look at a second order system. Just again, a very simple system. Instead of one mass, I have now another mass attached to it by a spring, and I have fixed the other end by another spring. And these are the equations of motion. So let's look at the first one. If I take y1 and pull it forward in the positive direction, I'll have a resistive force from the first spring. And if I take the second one and pull it forward, I'll have a force that is helping my first mass by the size of the force depends on the difference between the two lengths. And similarly for the second mass. So these are my equations of motion. This is a second order system, or sorry, 2 degree of freedom system. For each of them I have a second order differential equation. So in total it's a 4th order system, which means I need to have 4 states, and I have chosen my states to be position and velocity of the first mass and the position and velocity of the second mass. So with these state definitions, I can take derivative x dot 1 is going to be y dot 1, which y dot 1 is x2. X dot 2 is going to be y1 double dot. So it's this, which is going to be k over m. I'll have minus 2 k over m times y1 times x1 plus 1 k over m y2, which is x3. Similarly for this one, x dot 3 equals y dot 2, which is x4. And the last one, x dot 4 becomes y double dot 2, which is this. So I'll have, what do I have? K over m, y1, which is x1, minus 2k over m, y2, which is x3. So these are my state equations. And do I have, let me write it here. So my A matrix that I need to work with is 0, 1, 0, 0, minus 2k over m. We do have 0, k over m, 0, 0, 0, 0, 1, and k over m, 0, minus 2k over m, 0. Okay, that's my state matrix. I want to do the same kind of frequency analysis to see what are the natural frequencies of the system and what are the modes of oscillation, the same way we did before. To do that, I think we have solved this problem before. We get to, let's see. So I need to find the eigenvalues of this. So to do that, I need to solve for the determinant of a minus lambda I equals 0. I need to solve this. This is A. But this is well, maybe it's not too bad. It is doable. But let's use MATLAB to do that. So you'll have only these two things. It's going to be possible, but maybe I give it as an exercise in class. But if you solve for the eigenvalues, it is going to turn out. So this is a 4 by 4 matrix. So we'll have 4 eigenvalues and 4 eigenvectors. And as it turns out, there will be complex conjugate pairs. So lambda 1 is going to be j square root of k over m. And lambda 2, let me put it this way, lambda 1 and 2 are the complex conjugate pairs. And let me write it here. Lambda 3 and 4 are also going to be complex conjugate pairs of j square root of 3k over m. So this one is plus minus j omega 1 plus minus j omega 2. So already I have calculated the 2 natural frequencies of the system. So one of them is k over m, the one that kind of we had before, similar form. And the other one, or these show up because I have chosen the same k's and same m's. So that's why they turn out rather nicely. But anyways, I have 2 modes of oscillation. One mode oscillates at omega 1. The other mode oscillates at omega 2, which is square root of 3 times the other one. And associated with these eigenvalues, I have eigenvectors. Eigenvectors 1 and 2 equals, so I have, let me, what do we do? Let me write it this way. I don't want this. So let's only take the positive ones. And 3 also the positive one. So, because I don't want to confuse myself. So the first eigenvector associated with that positive eigenvalue is 1 j omega 1, 1 j omega 1. And the eigenvector associated with this one is going to be minus 1 minus j omega 2, 1 j omega 2. And the ones that for the eigenvectors related to the complex conjugate versions, the complex ones flip sign because they will be complex conjugate as well. So here's the funny thing. So associated with this mode of oscillation, I have a kind of complex, an eigenvector where the positions and velocities have the same sign. For both degrees of freedom. So let me add another item here, that the full solution y of t, did I have y? No, x. My state solutions. My x of t, my full solution, will be some linear combinations of c v1 e to the lambda 1 t plus c2 v2, which is complex conjugate pair of lambda 1 t plus c3 v3 e to the lambda 3t plus c4 v3 e to the lambda bar 3t. So this is the full solution. Depending on what is the initial condition of the system, you can find these C1s and C2s, but essentially you are linearly mixing these modes of oscillation. And because all lambdas are purely complex numbers, purely imaginary numbers, these e to the lambda t's are pure rotations that rotate the vectors v's, v1 and v3 and their complex conjugate pairs. So these vectors, when I plot the phasors, will be rotated depending on what initial condition is. So I'm going to again plot the phasor. This is the phasor. So again, remember what they represent. This one is for position y1. This one was velocity y1. This one was position y2 and velocity y2. Same for here. The first one y1, y dot 1, y2, y dot 2. Now plotting these phasors. Do I color code it? Let's try to color code it. Let's make these ones red. How many colors do we have? This one red. This one blue. J omega 1. Another one. This one, let's make it orange. And I don't know if this green works. Oh, well, this is good. J omega 1. So this one is just a simple real number. So this is my. Oh, you can't see. Not exactly. I can see it, but I don't know why you can't see it. Okay, that's good. And I'm going to just continue my axis like that. Okay, that's the first one. The second one is blue. It is arrows to make it nicer. That's y1. This one is y dot 1. y2 is in the same direction as y1. And we'll color this one this color, and y dot 2 is also in the same direction. So as these phasors rotate, you'll see positions are in the same direction. They have the same sign. So essentially they move together. So the two systems, this is the mode of oscillation. The positions are rotating together, and both of the velocities are 90 degrees ahead of them. If I want to plot the same thing, where is it? Oh, okay, let me do this. That's better, okay. These are my axes. So let's plot them again. This one is red, -1. This one is blue, minus j omega 2. This one is orange, and that one is whatever color it is. So position, the first one is a negative one, so this is y1. My y dot one is in the negative, this is y2, y dot 1, sorry. And this color is y2, it's positive. And lastly, the velocity is y dot 2. So now take a look at what happens here. The two positions oscillate opposite of each other. So as one of them goes this way, the other one goes that way. So essentially, the mode of oscillation is this. The positions are in opposite directions, so as one goes this way, the other one goes that way. So are the velocities, but also note that always the velocities are 90 degrees ahead of the positions, which should physically make sense. Or this is the physics that velocities in oscillations has to be 90 degrees ahead of the positions. But by looking at these phasors, here both of them are in same direction. So as one goes to the other one goes in the same direction. The first mode of oscillation is this. Essentially, the middle spring becomes ineffective. Both of them move together. The second one, which oscillates faster, is this. And all three of the springs are active in this case. And perhaps because of that, the system is more stiff and it oscillates faster at square root of 3 times the other natural frequency of the system. So by looking at what are the eigenvalues and eigenvectors of the system dynamics, we can find out what are the frequencies and also what are the modes of oscillation. Something that was perhaps not super intuitive from transfer functions, but looking at these systems, looking at the state space representation, it is a lot easier to visualize and understand the oscillations. So you can extend this to more degrees of freedom. The procedure is the same, and you can continue visualizing it the same way. A few notes if I have damping. So I'll have some terms here associated with the dampings. And in this case, I don't think the velocities would be exactly 90 degrees ahead, and these two would not exactly be opposite of each other. There could be some angle between them, meaning that you would have some kind of a little bit funnier motion. That's one thing, that if you have damping, these angles might change. The other one, going back to this full equation, usually the response of a system is, depending on the initial condition, is a combined version of the two modes of oscillation. And you have to very precisely choose your initial condition just to excite only one mode of oscillation. So that is another thing that we can have in mind. So other than that, I don't think there is much more else to talk about, at least right now in the context of this course on state space analysis. Well, that is all I have for now. And with this, we wrap up this section and we finish the state space representation. And the only thing that we will cover shortly after is a little bit touching on control systems and how we can design controllers to make our dynamical systems the way we want them. So until then,